It has never been anything but that, balance. Gravity and motion, energy and entropy, particles and waves. Yet we've layered these simple truths with complexity, tangled in equations and interpretations. One conspiracy folds into the next. But beneath all the noise lies a single question echoing through the void. What truly defines our universe? To answer that, we must plunge into the subatomic realm, where particles blink in and out of existence, where reality is more probabilistic than solid. It's not a world we can see, but it's the world that makes everything else possible. Physics isn't just a subject. It's a map. A way of peeling back the layers of the visible to glimpse the hidden architecture of existence. And no place on Earth has dared to peel those layers further than CERN. Founded in 1954 near Geneva, CERN, the European Organization for Nuclear Research, was built not just to understand the universe, but to unify humanity through the pursuit of pure science. It became the home of particle physics. A cathedral of data, accelerators, and unrelenting curiosity. Its early achievements were groundbreaking. In 1958, CERN confirmed the decay of the pion particle into an electron and a neutrino, validating predictions of the weak nuclear force. But that was merely the prelude. By the 1970s, CERN pushed deeper. The intersecting storage rings made history as the first facility to collide two proton beams head-on, an idea that changed everything. For the first time, scientists could reach energies high enough to simulate conditions from the earliest moments after the Big Bang. And then came the Large Hadron Collider, the crown jewel. A 27-kilometer underground ring stretching across the border of France and Switzerland, buried 100 meters below the surface. Here, particles are accelerated to 99.999999% the speed of light, then smashed together in a spectacle of controlled chaos, creating conditions not seen in 13.8 billion years. How? The LHC relies on superconducting magnets cooled with liquid helium to just above absolute zero, 271.3 degrees Celsius, making them colder than the vacuum of space. These magnets guide beams of protons with unimaginable precision. When they collide, they release energy equivalent to 14 tera-electronvolts, unleashing showers of exotic particles that last less than a blink of an eye. Tracing these events requires machines of equal wonder. Enter the detectors. ATLAS, CMS, ALICE, and LHCb, gigantic instruments weighing thousands of tons, layered like digital onions, each slice capturing specific behaviors. ATLAS and CMS, working independently, confirm discoveries. ALICE studies the quark-gluon plasma, a state of matter from the first microseconds of the universe. And LHCb investigates a fundamental asymmetry in the universe. Why everything exists as matter, when equal amounts of antimatter should have been created. But recording events is just the beginning. The LHC produces roughly 1 million terabytes of data every single day. Only a tiny fraction is stored. Algorithms filter the noise in real time, hunting for anomalies, rare, unexplained patterns that could point to new physics. That's how the Higgs boson was discovered. For decades, it was the missing piece in the Standard Model, the field particle that gives mass to others. But it was a ghost, decaying into forms difficult to trace. Only by comparing billions of collisions did physicists isolate the few that mattered, 2 gamma photons emerging in a specific pattern, with no clear source in the tracker. In 2012, after half a century of searching, the Higgs was real. It was a seismic moment. But the questions didn't stop. Because as monumental as the Standard Model is, it's still incomplete. It doesn't explain gravity. It doesn't account for dark matter, which bends light from galaxies but remains invisible. It says nothing of dark energy, which accelerates the expansion of the cosmos. Nor can it fully reconcile with quantum mechanics' stranger aspects, entanglement, decoherence, and observer-based phenomena. And now, something curious is happening. Over the past several years, data from LHCb has revealed anomalies in quark behavior. When beauty quarks decay into lighter particles, such as electrons or muons, they're supposed to do so in equal proportions. That's called lepton universality, a sacred rule in the Standard Model. But that's not what's happening. Muons are showing up more often. The symmetry is breaking. The implication? There may be a fifth fundamental force, one beyond gravity, electromagnetism, and the strong and weak nuclear forces. Some theorists believe this new force could be mediated by an as yet undetected boson, similar to the Z boson but even more elusive. If confirmed, it would mean our understanding of matter, energy, and the very fabric of space is missing something profound. And maybe it's not just forces we're missing, but entire frameworks of reality. The Standard Model might be a subset of a much broader system, just as Newtonian mechanics gave way to Einstein's relativity. CERN could be standing on the edge of that next revolution. It's no longer just about what particles exist, but what rules govern their existence. And whether those rules are constant or emergent. Are we seeing signs of supersymmetry? Are particles decaying into dark matter candidates? Are extra dimensions curled up in Planck-scale spaces, waiting to be glimpsed through high-energy collisions? For now, we don't know. But we're watching. And listening. This is more than physics. It's a hunt for the operating system of reality. For the hidden logic behind the universe. Maybe even for the fingerprints of something greater. CERN's mission has always been to push the boundaries of knowledge. But now, it's pushing at the very limits of the knowable. And somewhere, deep in the silence between collisions, the universe is whispering a secret we've only just begun to hear.